This is lesson 4.1, graphing polynomial functions. So a few terms you should be familiar with here in this section. A polynomial is a monomial or the sum of two or more algebraic terms. So let me give you an example. An example would be something like 2x squared minus x plus 5. That is an example of a polynomial. Another one would just be x minus 1 or 7x cubed minus 2x squared plus 4x minus 3. That's also an example of a polynomial. But what all of these examples have in common is that the exponents are positive whole numbers. Okay, so that's basically the main thing you're looking for when you're trying to determine if an expression is a polynomial. Okay, make sure that all of your exponents are whole numbers and that they're positive. If that is true, then you have a polynomial. Now, when you graph polynomials, they're going to be smooth curves. Okay, they're going to be continuous. Now, what that means is that you're going to be able to draw the curve without ever lifting your pencil or writing utensil. Okay, so if you can do that, then you have a polynomial function. Now, polynomial functions are always rising and falling. So an example would be something like this. Okay, so as you can see, it rises, reaches a maximum point, it falls, reaches a minimum point, and then rises again. Okay, so they're constantly rising and falling. There are no horizontal segments. Okay, there are no sharp corners. All right, and then end behavior. End behavior is what happens at the tail ends of a polynomial function. Okay, so for example, the polynomial that I drew, the example, falls on the left side. That's what the arrow is doing. On the left side, it's going down, it's falling, and on the right side, it's rising. Okay, so that's the very first thing we're going to go ahead and review under the core concepts. Under the core concepts, you see end behavior of a polynomial function. Okay, so let's go ahead and look at this. Okay, so here in these quadrants, they have summarized end behavior for all functions. Okay, so the nice thing about polynomials is that they tend to behave the same way. Okay, so the nice thing about polynomials is they behave in consistent ways. What I mean by that is if your degree, the biggest exponent in your polynomial, is odd and your leading coefficient is positive, they will all behave the same way, which means that they're going to fall on the left and they're going to rise on the right. Fall on the left and rise on the right. Okay, and it's perfectly okay to describe the end behavior using words or symbolically the way they just did it here for you. Okay, all right, now symbolically, the f of x is what the graph is doing. Okay, so it says f of x, the arrow means approaches. F of x approaches negative infinity because the graph is going down. As x approaches negative infinity, that's because you're on the left side of the coordinate plane. Now on the right side, f of x, the arrow's going up. So f of x is approaching positive infinity as x approaches positive infinity. So because you are on the right side, x is approaching positive infinity as well. Okay? Now, if the degree is odd, but your leading coefficient is negative, then it flips. Okay, it does the opposite. On the left side, the graph rises, and on the right side, the graph falls. So this time you say it rises left and falls right. Okay, again, symbolically, the graph is going up, so we say f of x approaches positive infinity as x approaches negative infinity. Again, the second part tells you what side you're on. Okay, we're on the left side, so x approaches negative infinity. Now on the right side, the graph is going down, so f of x, the function, is approaching negative infinity as x approaches positive infinity. Now remember, another way to think of f of x is y. What are the y values doing on the right side? The y values are getting smaller because it's going down, and that's why it's approaching negative infinity. And you're on the right side, so your x values are getting bigger. Okay, now if we look at even degree polynomials. Even degree polynomials. First, let's look at an even degree polynomial with a positive leading coefficient. Think of a parabola, okay? You're very familiar with parabolas. Parabolas with positive leading coefficients open up, okay? That means that both tail ends are rising. They're both going up. So here you can say rises left and rises right. Okay, rises left and rises right. Okay, and again, symbolically, the graph is going up on both sides. That's why f of x is approaching positive infinity. On the left side, f of x always approaches negative infinity. X always approaches negative infinity. And on the right side, x always approaches positive infinity. Okay, and the last scenario is when you have an even degree function. That means it's degree 2, 4, 6, or 8, and your leading coefficient is negative. Okay, think of it as a parabola that opens down. Parabola that opens down is going to have both tail ends pointing down. So f of x is approaching negative infinity. Once again, when you're on the left side, x approaches negative infinity. When you're on the right side, x approaches positive infinity. So if you want to describe using words, you would just say falls left and falls right. Okay. All right, so I'm going to go ahead and pull up decimals and show you how this really is true. Okay. Now notice that in between they have this dotted or broken sort of graph. This is just an example. Okay. They're not all going to behave that way. In the middle, they are going to behave many different ways, okay? And we don't care what happens in the middle right now. All we're looking at is the tail ends, just what happens at the ends, okay? Again, these are just sample graphs of what may happen in the middle. It doesn't mean it's going to happen every time. Okay, so now I'm going to go ahead and use decimals just to show you that all odd degree functions with positive leading coefficients do tend to behave the same way. Okay, so let's start with x to the third power. Okay, actually you should have started with just x. Okay, x we know is a line that with a positive slope, which means that it rises from left to right. So right here, it rises on the left side and it falls on the right. Sorry, yes, it rises on the right and falls on the left. Now, x to the third power okay, again, the graph itself is different, right? What happens in the middle is not the same, it's different, but as you can see, it rises on the right and it falls on the left. Okay, let's go ahead and try x to the 5th power. X to the 5th power. Okay, again, as you can see, it basically looks like an S shape. Okay, an S shape. It also falls on the left, rises on the right, and let's try just one more odd power, x to the 7th. Okay, again, as you can see it, sorry about that, it rises on the left, rises on the right, falls on the left. Okay, so again, as you were able to see, all of these basically behave exactly the same way. Okay, all right, now if we put a negative in front of each one of these, everything's going to become the opposite. Okay, everything will become the opposite. It'll rise on the left and it'll fall on the right. Sorry about that. Okay, so there you go. So these are power functions, and that's why they have almost the same exact shape. They have an S shape except for the linear function. Okay, but once we start adding more terms, so if I start adding, for example, x squared and minus x, maybe an x to the 4th power. Okay, what happens inside starts changing. You can't really see it here because I haven't zoomed in enough, but that doesn't matter. Okay, again, we don't really care about what happens in between, okay, the tail ends. We're just looking at the tail ends. Again, if your leading coefficient is negative and you're graphing an odd power, odd degree function, it's going to rise on the left and it's going to fall on the right. Okay, let's go ahead and now look at even degrees. Let me go ahead and get rid of each one of these graphs. Let's look at even degrees, okay? Even degrees with positive leading coefficients, x squared, x to the 4th, x to the 6th power, okay? As you can see, they all rise on the left and rise on the right, okay? They all look slightly different in between, okay? But the end behavior is the same for all of them. And if we just change all the leading coefficients to negative, then they're going to do the opposite. They're going to fall on the left and fall on the right. Okay, so there you go. All right, so let's go ahead and just review how to classify polynomials. Okay, how to classify polynomials. So let me move this out of the way. All right, so you can classify polynomials based on their degree. Okay, so if you have a polynomial of degree 0, okay, we call it a constant. Okay, that means that it doesn't have a variable attached to it, okay? And I'll give you an example in a sec. And if you have a polynomial of degree 1, we call it linear. If you have a polynomial of degree 2, we call it quadratic. If we have a polynomial of degree 3, we call it cubic. Degree 4 is quartic. Degree 5, we call it quintic. Anything after degree 5, we'll just call it degree 6, degree 7, degree 8 polynomial. Okay? All right, now examples. Okay, constant is just a number. So for example, -3. Linear can be something like x plus 4. Okay, the degree is 1. That's what we call it linear. Quadratic can be x squared minus x squared minus 2x plus 1. Cubic can be 2x cubed minus 4x squared plus x minus 3. Quartic can be x to the 4th minus 16. And quintic can be x to the 5th plus x to the 3rd minus 1. Okay, these are just examples. Again, what makes the first one a constant is the fact that it doesn't have an x. What makes the second example linear is the fact that it's x to the first power. Quadratic, x to the second power. The 2 is the biggest exponent. For the cubic, the 3 is the biggest exponent. For the quartic, the 4. And then for the quintic, the 5 is the biggest exponent. Okay, so the biggest exponent determines the degree of the polynomial. You can also classify polynomials based on the number of terms they have. Okay, so based on the number of terms, if it has one term, we call it a monomial. If it has two terms, we call it binomial. If it has three terms, we call it a trinomial. 4 terms, it's a quadrinomial. And anything after 4, so I'll say 5 plus, anything more than 5 terms, we can call it a polynomial. Sometimes when it has 4 terms, it's also referred to as a polynomial, okay? So we just stop giving them specific names, okay? So they just fall under the general name polynomial. All right, let's go ahead and look at some of the examples. Okay, so examples 1 through 4. You have to decide whether the function is a polynomial function. Whether the function is a polynomial function. If so, write it in standard form, state its degree, type, and leading coefficient. Okay, and just a reminder that standard form means that you are writing it from biggest degree to smallest. Okay, so for number 1, first thing I'm going to look for is the exponent. I'm going to look at the exponents. +2, +4, +1. All of my exponents are positive. They're all whole numbers. That means this is a polynomial. It is a polynomial. Now I'm going to go ahead and write it in standard form. Okay, so from biggest degree to smallest. So the first term should be -3x to the 4th. And then 2x squared. And then the 6x. And then the 1. Okay. And the degree is the biggest exponent. So the degree is 4. The type, it's degree 4, so we call it quartic. And it has 4 terms, so I'm going to call it a quadrinomial. Again, I can also just call it a polynomial. And the leading coefficient is -3. Okay, leading coefficient, the coefficient in front of the term with the biggest exponent. All right, so example number 2. Again, first thing I look for is all the exponents, making sure that they're positive. So it has x cubed, so far looks good. But then it has 7 over x, okay? And that, they're trying to trick you, because 7 over x is really (7x to the -1 power). Okay, so it's a little deceiving. Okay, it makes you think that all the exponents are positive, but really the x has an exponent of -1, which makes this not a polynomial. So I don't have to worry about answering any other part of the question. It's not a polynomial, so I can't classify it. Okay. All right, number 3. There's only one variable. It's right here, x, and it's x to the first power. That's a positive exponent. Therefore, this is a polynomial. Okay, it is already in standard form, so I don't have to rewrite it. The degree is 1. Okay, the leading coefficient is square root of 15. And it has, let me see, so because it's degree 1, we call it linear. And it has 2 terms. So it's a binomial. Okay, that's it for question number 3. Question number 4. Again, first thing we look for is the exponents. X squared, that's good. X to the first, that's good. And this is a constant, so no x. That is definitely a polynomial. It is not in standard form, so let's go ahead and write it in standard form. It should be negative 2x squared plus 3x minus 2 root 3. The degree, the biggest exponent, is 2. Because the degree is 2, we call it quadratic. It has 3 terms. 1 term, 2 terms, 3 terms. So it is a trinomial. And the leading coefficient is negative 2. Okay? All right. Next 2 questions, 5 and 6. You're asked to evaluate for the given value of x. So that's just plugging in. Okay? So for question number 5, they want you to plug in x equals 2 or substitute in x equals 2. So h of 2. Oops, sorry, positive 2. Don't know why I wrote a negative. So substitute in a positive 2. And then follow order of operations to evaluate. 2 to the third power is 8. The negative in front of it makes it a negative 8. 2 to the second power is 4 times negative 2 is negative 8. 3 times 2 is 6 plus 4. And then if we just combine all these numbers from left to right, we are going to get negative 18. All right, same thing for number 6. This time we want you to evaluate it for negative 4. G of negative 4, so substitute in a negative 4 and follow order of operations. PEMDAS. If the numbers get too large, go ahead and use a calculator. So negative 4 to the 4th power is 256. Negative 4 to the 2nd power is 16 times negative 32 is 512 plus 256. If you add these numbers, this equals 0. Okay? All right, questions 7 and 8, they want you to describe the end behavior of the graph. Okay? So you're not being asked to graph, you're just asked to describe the end behavior based on the degree of the polynomial and its leading coefficient. So first thing I check is to make sure that the polynomial is given to me in standard form. Sometimes they will try to trick you, and if you're not paying attention and you just look at the first term, you may get it wrong. So in this case, they were kind. They gave it to us in standard form from biggest exponent to smallest. The degree of the polynomial is the biggest exponent, so it's degree 6, which is an even power. And your leading coefficient is negative 3, which is obviously negative. So whenever I think of even degree polynomials, I always think about the parabola, okay? So I think of this as a parabola that opens down. So a parabola that opens down means that it's going to fall on the left and it's going to fall on the right. Again, you can write it in words. Falls left, falls right, or you can write it symbolically. F of x approaches negative infinity on both sides. Both tail ends go down. And we're on the left side, so as x approaches negative infinity, and on the right side as x approaches positive infinity. Okay? All right. Number 8, not in standard form. So I'm going to look for the term with the biggest exponent, and that happens to be right in here. All right, so that term is going to determine the end behavior of the function. The degree is 5, which is an odd degree, and the leading coefficient is 3, which is a positive leading coefficient. Okay, so whenever I think of odd degrees, I think about a line, okay, because odd degree functions behave the way a line behaves. Okay, so this I think about as a line with a positive slope. So I know that it's going to rise on the right side, and I know it's going to fall on the left side. So again, we can use words to describe it. Falls left, rises right, or symbolically, we would say f of x approaches negative infinity as x approaches negative infinity. And on the right, f of x approaches positive infinity as x approaches positive infinity. Okay, that is question number 8. Question number 9. All right, they want you to describe the degree and the leading coefficient of the polynomial function based on the graph, okay? So anytime you have tail ends that are doing the opposite, where one is going up and the other one's going down, automatically it has to be an odd degree, okay? So that's the behavior of odd degree functions. So this is an odd degree. And because it's rising, basically if we connect the two arrows, the tail ends, okay, it looks like it is falling from left to right if you connect the tail ends. So this has to be a negative leading coefficient. Because it's rising left and falling right. Okay, that only happens when you have a negative leading coefficient. All right, let's go ahead and move on to the next page. Oh, I'm so sorry. Okay, for questions 10 and 11, you're asked to graph a polynomial function. Okay, so we are going to use end behavior and a table to sketch the graph. So based on the degree of the polynomial, this is degree 4. It's an even degree. And the leading coefficient is -1. We know that the end behavior indicates that this graph should fall on the left side and it should fall on the right side. Okay, now let's go ahead and create a table of x and y values. All right, so I'm going to choose the numbers I always choose. I'm going to choose -2 negative 1, 0, 1, and 2 as the starting point. If that produces the correct end behavior, then I am done. Otherwise, I'm going to go ahead and add additional points. So if we plug in negative 2 into the function, negative 2 to the 4th power is 16. 16 minus 16 is 0. If we plug in negative 1 to the 4th power is 1. 16 minus 1 is 15. If we plug in 0, 0 to the 4th power is 0. 16 minus 0 is 16. If we plug in 1, it's going to be 15. And if we plug in 2, it's going to be 0 because of the symmetry this graph has. Now we are ready to create a graph. So let's go ahead and draw our XY plane. Alright, so I'm going to go ahead and use a scale of 4 on the y-axis and a scale of 1 on the x-axis. And let's go ahead and plot these points. Negative 2, 0, negative 1, 15, 0, 16, 1, 15, and 2 is 0. Okay, so as you can see, this basically looks like a parabola. So connect with a nice smooth curve. Okay, just be aware that you will need a minimum of at least 5 ordered pairs to graph polynomials, sometimes more. Okay, in this case, plotting 5 points gave me the correct end behavior. It falls on the left side and it falls on the right side. Okay, so I get to go ahead and move on to the next question. All right, question number 11. The degree here is based on the term with the biggest exponent, which is right here. Go ahead and box it in. Degree is 5, and the leading coefficient is 3. So odd degree, positive leading coefficient. So based on the end behavior, we expect this to fall on the left and to rise on the right. Okay, so just like we did for the previous one, we're going to go ahead and create a table of x and y values. And I am going to start with the same numbers, negative 2 to positive 2. Most of the time that will work for me. If it doesn't, I will go ahead and add additional points, additional x values that are smaller than negative 2 or larger than positive 2. Okay, and I will know that this is correct if I get the correct end behavior, that it falls on the left and rises on the right. If I plug in, let's start with 0. It's the easiest number. If we plug in 0, we're going to get 0. If we plug in 1, we're going to get 1 plus 3, which is 4. 4 minus 1, which is 3. If we plug in 2, 2 squared is 4. 2 to the 5th power is 32 times 3 is 96. Plus 4 is 100. Minus 2 is 98. That is a huge number. But at least we know that it's going in the right direction because that number is big. That means that it's rising on the right, which is what we expect. If we plug in negative 1 squared is 1. Negative 1 to the 5th power is negative 1 times 3 is negative 3. Negative 3 plus 1 is negative 2. Negative 2 minus a negative 1 is negative 1. And if we plug in negative 2 squared is 4. Negative 2 to the 5th power is negative 32 times 3 is negative 96. Negative 96 plus 4 is negative 92. Negative 92 minus a negative 2 is negative 90. Okay, so let's go ahead and draw our xy plane. Now just know that these graphs, although we're plotting points, are not going to be perfect. They're not going to be exact. We really would need a lot more additional points in order to get a more accurate graph. Alright, so let's go ahead and use a scale. Just going to go ahead and use a scale of 1 on both the x and the y axis. I know that the 98 and the negative 90 will not fit, but that's okay. Alright, so let's go ahead and plot our points. Negative 2, negative 90 is way somewhere down here. I know it's a lot lower, but that's okay. At least I know it's going down. Negative 1, 0, 0. 1 is 3. And 2, 98 again, somewhere really high up there. Okay, so it's going to rise on the right side and it's going to fall on the left side. Okay, again, not perfect. If you plug it into decimals, it might not be exactly correct, but it's pretty good indication of what the graph will look like. Okay, again, in this section, the most important part for us is the end behavior. Are we getting the correct end behavior? And we are. Okay, there are no sharp corners. There's no sharp corners. It is rising and or falling. Okay, and it is in this case falling on the left side and rising on the right side. Let's go ahead and move on to the next one. All right, question 12. They are describing a polynomial function and you have to sketch what you think this is going to look like. Of course, not everyone's sketch will look exactly the same. Okay, so what I'm going to give you right now is just a sample graph. Okay. All right, so question 12. Sketch a graph of a polynomial function if f is increasing when x is less than negative 1 and also between 0 and 1. F is decreasing when x is between negative 1 and 0 and when it's greater than 1. And f of x is less than 0 for all real numbers. Okay, so based on this, the most important thing I see here right now is this part here. F of x is less than 0 for all real numbers. Remember that f of x is y, right? So basically it's saying that y is less than 0. It's saying that y is always negative, okay? So what this means is that when we draw this function, our graph will always be below the x-axis, okay? So that's important. The graph is always going to be below the x-axis. Okay, so I'm not really showing quadrants 1 or 2 because our graph is not going to exist there. And then they are telling us that it's increasing and decreasing between negative 1, 0, and 1. So I am going to draw just some lines for me just so I can, okay, so I'm going to call this negative 1. Okay, so I know that between here and 0 and 1, my graph will increase, decrease, increase. Okay, because that's what they're describing. The lines are just for me as guides. Okay, so now let me start sketching this. Okay, so it says f is increasing when x is less than negative 1. So when it's less than negative 1, it's increasing. So it's going up. Going up, it's going up, it's going up. It reaches some point. I don't know how far up, and it doesn't matter, but I know it has to be below the x-axis. Okay, so I sort of graph this part right now. And then it says it decreases between negative 1 and 0. So between -1 and 0 decreases. I don't know how far down, but it'll decrease. Okay, and then it increases again between 0 and 1. Increases again between 0 and 1. Again, I don't know how high, and it doesn't matter as long as I stay below the x-axis. And then it decreases when x is greater than 1. Okay, so that's basically what they described. Again, there's no correct answer. There's infinitely many correct answers as long as your graph is below the x-axis, because it said that f of x has to be less than 0 for all real numbers, and as long as we showed that it's increasing when x is less than -1, and between 0 and 1, decreasing between -1 and 0, and when x is greater than 1. So based on this, because my tail ends both go down, I know this has to be an even degree polynomial. Okay, so it has to be an even degree, and because they go down, because the tail ends go down, it tells me that the leading coefficient must be negative. Okay, all right, and that's all I know. Okay, I don't know anything else more specifically than it's an even degree, leading coefficient is negative. All right, so that's it for question 12. Now the last question, question 13. All right, question 13. It says the number of students, S, in thousands, who graduate in 4 years from a university can be modeled by the function S of t, where t is the number of years since 2010. So they want you to use the graphing calculator to graph a function for the interval between 0 and 5. Describe the behavior of the graph on this interval. Okay, so let me go ahead and pull up decimals. Give me 1 second. Okay, so I went ahead and I graphed the function S of t on decimals between the time 0 to 5. Okay, that's the interval that was given to you here. And as you can see, it looks like it falls on the left side. Okay, and if I change if it says 0 to 5, but if I change it just a little bit, if I change it to -1, okay, the end behavior changes. Okay, so that's why they specifically said they want the end behavior just from 0 to 5. Okay, so from 0 to 5, it looks like, and it's very slight, but it looks like it's sort of falling on the left side and falling on the right side. Okay, all right, so let's go ahead and continue. That answers part A. Okay, it says again, describe the behavior of the graph on this interval. Okay, so it seems to, the graph itself appears to increase, and then reaches sort of a maximum point, and then it starts decreasing. All right, so based on what we saw on decimals, it looks like the number of students graduating from college in 4 years increased initially, and then the number of students graduating in 4 years started to decrease. Okay, so that would answer part A. Okay, so once again, the number of students graduating from college initially increased, and then it looks from the graph that around 2012, the number of students graduating in 4 years started to decrease. Okay, for part B, the average rate of change in the number of 4-year students graduating from 2010 to 2015. So remember that average rate of change is just asking us for the slope. So we need 2 ordered pairs. They're giving you the x values. Okay. We're getting the x values, and we have to plug it in to get the y values. Okay, so the average rate of change in the number of four-year graduates from 2010 to 2015, remember that 2010 is what they're calling year zero. Okay, so this is T is 0, and 2015 is 5 years later, so this would be T is 5. So we have the X values of each coordinate. We need the Y values, so we're going to plug these numbers in to the function that was given to us. So S of 0, we're going to go ahead and plug in 0. Okay, when we plug in 0, we get 23. So one of our order pairs is 0, 23. And then we're going to go ahead and plug in 5. And if you plug in 5 and you plug it into your calculator, you are going to get approximately 16.75. Okay, so a second order pair is 5, 16.75. And now you're going to plug it into the slope formula. Okay, so 16.75, the change in y over the change in x, 16.75 minus 23 over 5 minus 0 is going to equal approximately negative 1.25. Okay, so the negative rate of change tells us that the number of graduates is decreasing. Okay, it's decreasing. And remember that this number is in thousands of dollars. Sorry, in thousands of students. So what this tells us is that there's approximately 1,250 less students graduating. Okay. Oops. Students graduating. In 4 years. Every year. Okay. So about 1,250 fewer students graduating in 4 years every year. Okay. All right. Part C. Do you think this model can be used for years before 2010 or after 2015? Explain your reasoning. So I'm going to pull up decimals one more time. Let me go ahead and pull this up. Okay. So let me go ahead and bring up decimals. Let's see what this model looks like before 2010, which we glanced at it briefly, and years after 2015. So I'm going to go ahead and change. So let's see what it looks like before and after. Okay. So I'm going to say about negative 5. Let's say about 20. Okay. So as you can see, before the year 2010, which would be our negative values, it seems to have a pretty sharp decrease. Okay. And there are many variables that can account for that. Okay. Okay, for example, right now we're going through a pandemic. If we graph the number of graduates that are graduating in 4 years based on the data, there may be many students who do not like learning online. You may have students that are postponing graduating because they want to go back to in-person classes. So you may have a sharp decrease like this. Okay, and also after 2015, there's another very sharp decrease. Okay, so that doesn't necessarily make sense for the context of this problem, and that's why they limited this model to just the years between 2010 and 2015. because it only made sense for those years, okay? So just know that when you use mathematical models, they're not always going to hold true. That's why you limit the domain, okay, to only numbers that make sense to the context of your problem, okay? All right, so let me go ahead and move this. Also, in this particular case, if we look at this decimals graph, it keeps going down, okay? Once this dips down below the x-axis, it doesn't make sense that you have negative number of students graduating from college. So that's another reason why you would limit the domain of the function, okay? Again, you limit it to just the numbers that make sense to the context of the problem. Okay, that is it. That completes this lesson.